Today we're going to be talking about the iron-carbon phase diagram. This is a really key piece of information. I shouldn't say piece, whole field of information that is really key to understanding how steel works, but in this case we're referring specifically to Wootz and other crucible steels, or even just other homemade steels. And things you need to keep in mind when you're coming up with your formulas. I am going to be posting on my Instagram account, at Peter Burt Knives, some pictures of the phase diagram, and if I get into any other information, I'll try to remember to post some diagrams there to help illustrate that as well. Now I've drawn up kind of a crude, simplified version of the iron-carbon phase diagram. And we're going to first look at a few key things on here. So first, to understand it, we've got temperature running on this side. This is a pretty standard graph in many ways. And then carbon content across this axis. Now, the carbon content greatly changes what structures you're going to get at different temperatures. And essentially, this diagram tells you what structure you should have at a given temperature and a given carbon content. There's a giant caveat to that, though, which is this diagram is based on what they call equilibrium, which is basically holding the steel at temperature long enough for everything to sort of balance out. And in bladesmithing and blacksmithing, we're really never holding temperatures nearly long enough to achieve that. I mean, even in industry, they really don't hold temperatures that long. So that's the big caveat. Well, actually, second caveat, not quite as big. As you add alloys, it changes this diagram. To give you an idea, so first we'll just quickly say this sort of roughly triangular area here, this is where you find pure austenite. Now you can find austenite in other areas on this diagram, but this is where you have, theoretically, just austenite, nothing else. Let's say we start adding chrome to this steel. We start adding chromium to this steel. This area is going to shrink and get smaller and smaller until essentially the pure austenite region disappears completely. This is partly why 5160 needs to be quenched from a slightly higher temperature than, say, 1075 to achieve full hardness. It's partly that it is a lower carbon, so it's moved over this way a little bit, and is higher chromium content, so we've moved our pure austenite line up a little bit. So, and once you get to stainless steels, part of the reason that stainless steels have very, very specific heat treat requirements is because the area of pure austenite has become tiny. I do actually have a diagram of that, and I'll try to remember to post that in my Instagram account. So let's quickly kind of go over what our zones are here. So here we have, as I was saying before, pure austenite. Another basic zone up here, we've just got liquid iron. That's it, So it's liquid iron with, carbon floating around in it, essentially. Down here, once we get out of those, we start to get into mixed territory. And that is because carbon wants to exist really only in two different states in steel. That it would either like to be in solution, so dissolved, sort of like putting sugar into water, stir it up, bam, dissolves. So that would be in solution. Or it wants to exist as a carbide. Now, iron carbide obviously would be one, typically referred to as cementite. And the, and then you have the various alloy carbides, which we'll get into in a different discussion most likely. So down here we have at 0.8% carbon, roughly speaking, we have what's referred to as the Eutectoid point. Now, anybody who's done jewelry work, things like that, or maybe you've come across it anyways. Typically with metals you hear about the eutectic point, and the eutectic point is different. The eutectic point is the lowest possible melting temperature for a given combination of materials. So the eutectic point of iron and carbon is over here at about 4.3% carbon. That is the lowest melting temperature for this combination. Intriguingly, happens at about 1150 Celsius. And I'm going to do all my temperatures here in Celsius. The diagram that I'm going to post has both Celsius and Fahrenheit. I'm doing this in Celsius mostly because my pyrometer only reads in Celsius for some reason. It's, get things off Amazon, who knows what you'll find, right? So right now I'm a little more familiar with the Celsius. So again, that melting temperature, 1150 Celsius, the eutectic point, way over here, about 4.3% carbon. So here at 0.8% carbon, we have what is referred to as the Eutectoid point. And basically, this is where we have what, in some sense, you might call the perfect structure of steel. So this is, at this carbon content, you have, you can see the lowest point on the pure austenite field. So the coolest temperature at which you can hit pure austenite. At this temperature, you also have sort of the premium mixture of ferrite, which is essentially pure iron, and cementite, as I said before, iron carbide. And this takes the form of perlite. Now, this is a lot of different terms to toss out there. In essence, perlite is sort of a lamellar or layered structure of carbide, of iron carbide, and pure iron. The actual solubility of carbon in iron below this temperature here, critical temp as it's often referred, the solubility is incredibly low. You really, I don't remember what it is, but it's a fraction of a percent. So what happens as you hit this temperature, let's say we're cooling and we hit critical, otherwise known as A1 and A2. Depends on whether you're heating or cooling. Heating, I believe, is A1. Cooling is A2. So as we're coming down, we hit A2. And you will start to have the carbon, it's no longer soluble. It is getting rejected. It's getting kicked out. So what you get essentially is pure iron and then layers of pure carbide. This creates kind of a pearlescent appearance in micrographs, thus perlite. As we go to this side, as we have lower carbon, this is where you get the hypoeutectoid steels, meaning they are lower in carbon content than the eutectoid point. And to this side, up to 2.2% carbon, So between about 0.8% carbon and 2.2% carbon, we have the hyper-eutectoid steels. 2.2% carbon, theoretically, is the beginning of cast iron. Now, there are steels that really play with that line some, but you don't really see them much because you get into very frisky territory there. Below this, below this carbon content, below 0.8% carbon in the hypo-eutectoid steels, if you've slow cooled your steel, you're going to get a mixture of perlite and ferrite. So basically you've got perlite, which is your mixture of iron carbide and pure iron, and then areas of pure iron, the ferrite. And to the other side, you will have a mixture of perlite and just free carbide, not associated with the perlite structure. So, and the perlite structure is a fixed ratio of iron to carbon. So, which is why 0.8% is our eutectoid point. You get pure perlite at that point, equilibrium and all that. And to one side, you've got excess carbide. To the other side, you've got excess pure iron. So the reason that you need a higher temperature to get into the austenite, the pure austenite zone, to either side of that, is it takes a certain amount of time and temperature to dissolve that on this side excess ferrite, and on this side excess cementite. So that means that we've got these two zones in which on this side you have a mixed, because we've now crossed A1, we're heating up. So on this side we've got a mixture of austenite and ferrite, pure iron. And to this side we have a mixture of austenite and cementite, iron carbide. Now, when you cross this line, the ACM, you are crossing over into theoretically pure austenite. So whatever free carbide you had still floating around undissolved, theoretically now it's dissolved. Again, going back to that caveat, this is at equilibrium. Depending on how large your carbides are, depending on how fast you are heating, it's going to actually affect the location of this line. As I noted earlier, adding alloys affects the location of this line. So we're really going to be talking about the ACM line and this zone over here, which is really where we're talking about with Wootz, from about 1.3% carbon, maybe 1.2% carbon, up to about 1.8% carbon. Once you get past those, or get outside those two, you're really outside the historical carbon contents, and therefore, to my mind, you're outside the Wootz zone. Not to say you can't make steels outside that range, but I think it's fair to argue it's no longer Wootz. Similarly, Wootz is a super low alloy steel. So if you're making a high alloy steel, is it Wootz? I would say, obviously, in a strictly technical standpoint, no. For myself, what I typically do if I am outside the alloy content range, the historical alloy content range, I will often note that. So for example, I've made stainless Wootz. There was no stainless Wootz historically, but it's also difficult sometimes to describe what you're doing if you've got if you need to describe it too thoroughly, just to give it a name. Wootz, for most people, sort of summarizes that this is a small batch, high carbon steel, made in, a small furnace, not a large batch steel made in industry. But you know what? There's plenty of room for argument on that, but I'm not going to argue with you about it. So back to our diagram. Some other key things here. So your heating rate, obviously, that affects where your ACM line is. It also affects the cooling rate, same thing. If you are cooling quickly, your ACM line is going to move. You will continue to have austenite further down, and you will not be forming cementite or carbide until a cooler temperature, just because you are, depending on your cooling rate. And now the same thing is also true, as I was noting before, for A1 and A2. So that, theoretically, if you were cooling incredibly slowly, you will switch from, let's say we'll go back to the eutectoid steel here for a moment. You'll switch immediately from austenite to pearlite. This, in practice, this isn't how it works. As you're cooling, you are cooling fast enough that that line is depressed. It's pushed down to a cooler temperature. So you don't actually start to transform until a lower temperature. So now you may have noticed this in your forging. If you were heating a bar of steel and you get to a very dull red temperature and you start trying to forge it, there's a pretty good chance something awful is going to happen because you have not perhaps actually crossed over A1. However, when cooling, you will probably find that you could forge to a cooler temperature without having awful things happen because that transformation temperature is depressed. So, that's a way in which you can actually witness this line in your forging. The other way you can witness this line is that since there is a change in crystalline structure at this point, a lot of stuff moves around in order to make that happen. You don't really notice it during heating, but there is actually a pause in the temperature of your steel as your steel soaks up extra energy to make the shift, to make that crystalline structure change happen. You can more readily witness it in the cooling process, in which you get what's sometimes referred to as recoalescence, where as you are cooling, you start to approach this transformation, and the steel actually releases energy, which you see in the form of light, or a brightening of the steel, as it cools and that transformation occurs. So on the way up, you may notice it as, visually as, I guess I would say, a sort of stickiness of the color. You're heating and you find that the edge comes up to temperature and begins glowing really easily, but there's some sections in there that are just not apparently coming up to temp as fast as you would expect. What you're seeing is that pause as it is making the transformation. So, another key point on here from the perspective of Wootz is this right here. So here we are at 1150 C, roughly. Now, for all of this section out here, that is the top end of your forging temperature. So once you get past 2.2% carbon, you're absolutely limited by 1150 C. This is sort of, it's in the orange range, brighter end of the orange range. Now, how does this affect us what happens if you cross that? So basically, here we have the austenite zone. Here we have a mixture of austenite and cementite. And here we have a mixture of austenite and liquid iron. So this is often referred to as the mushy zone. I often refer to it as the wet sand zone. And if you forge in this range, since you have a partially liquid substance, it's going to mush. It will behave very poorly. It will not so much crack as just sort of tear apart, as though you've taken wet sand or wet soil and smushed it, and it just tears apart in terrible ways. So now this effect is referred to as hot shortness. And in case you're curious, short in this case refers back to I believe it's an Old English derivation, which means things that crumble. So for example, shortbread, a thing that crumbles. So hot short refers to steel that crumbles once it gets hot. Now, other things can affect that other than just the carbon content, but I'll get into that in another video. But something to know about this line is that defines your theoretical top-end forging temperature for a steel that has been rendered homogeneous. Now that's a key thing to remember, is steel that's been rendered homogeneous. So let's say we take our 1.5% carbon steel, which is generally about what I aim at. We follow that vertically, so we know where roughly the ACM line is, so where carbide disappears and we have pure austenite back and forth across that line during forging. And we theoretically know what that top end temperature is. However, Wootz is not homogeneous. So where that line is actually depends an awful lot on what your structures are. So if you have heated and you have a lot of carbide, and that carbide has just dissolved, and now you are preparing to forge, well, that carbide dissolved or partially dissolved, and you now have a concentration of carbon around the carbide. Intriguingly, the highest concentration of carbide or carbon that you can have held in the steel is 2.2%, or else you get liquid. So basically, if you trust this line implicitly, you might get into some fishy territory. The 1150C, that's essentially guaranteed unless you have some other impurities in there that affect this temperature, affect your hot short temperature. Prime among those would be sulfur, but again, we'll get into that in another conversation. So I think this is a good start on the iron carbon phase diagram. Gone over most of the basic parts of it. One thing to note on here, as just sort of a final thing, the A1 and A2 temperatures don't perfectly correspond to magnetic and non-magnetic. So using that as a reference, using non-magnetic as a reference temperature can be helpful, but it does not absolutely correspond to to the critical temperature, to A1. So little takeaway there if you didn't already know that. And I am also going to reiterate that this is for just the iron-carbon phase diagram. In your normal steels, you're going to have manganese. You will probably have things like chromium, vanadium, tungsten, also, all kinds of other alloying elements in there, and they all change this in subtle ways. So, the more alloying element you have, the more it changes this diagram. So, again, I'm going to post this along with a couple other pieces of information on my Instagram account. That is @PeterBurtKnives. You can also find it on my business Facebook page, Peter Burt Knives. And, I'm happy to answer questions either in the comments on the video or on the Instagram account. Quite honestly, I don't look at the Facebook page much, so don't ask me questions there. Hope this was helpful and you didn't fall asleep. Thanks.